Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will review an important concept from probability theory. We will talk about the expected value for a continuous random variable. We will talk about an example. We're going to be solving that example first, doing things by hand, and then I'm going to show you how to tackle that problem using R. Okay, let's get to work. So this is the problem I would like to solve with you. Okay, so in this case the random variable of interest is the proportion of time per day that all checkout counters in a supermarket are busy. Okay, so we have this expression f of y, this function equal to c times y squared plus 1 minus y, the whole thing to the fourth power, and that applies for y's between 0 and 1, and that function, that PDF, is going to be 0 elsewhere. Okay, so first let me remind you that as you can see from the way that f of y is defined, that density satisfies the first condition that a legit PDF, legit probability density function, must satisfy. It is non-negative. It's 0 or positive. Okay. In another video, we already mentioned this, and in sta313, right, in probability, you discussed that the other condition that a legit probability density function must satisfy is if it's a continuous random variable, the one that we are talking about, the integral from negative infinity to infinity of its PDF must be equal to 1, right? So that is the characteristic, right? The condition that we're going to be using to find that missing constant. Okay? So that's going to be used to solve part A. And then for part B, we are going to find the expected value of y. Remember that the expected value of y is just a numerical summary for that PDF. The expected value of a random variable is going to give us an idea of where the center of that PDF is. Okay? Okay. So, first, let's try and do part A by hand. Let me open a new one here. So, part A. As we said, what we're going to be doing here is using that property that if you have a continuous random variable, the integral from negative infinity to infinity of its PDF must be equal to 1. Okay? So, in this case, remember we only have something between 0 and 1, right? The PDF is 0 elsewhere. Okay. So let me be very specific here. We have the integral from negative infinity to 0 of 0 dy plus the integral from 0 to 1 of Now what we have is c times y squared times 1 minus y to the fourth power. So cy squared times 1 minus y to the fourth power dy plus, and now we have the integral from 1 to infinity of 0 dy. That must be equal to 1. Okay? Oops. So that must be equal to 1. We know that the only part that matters is the one in the middle, right? The integral from 0 to 1 of this. Okay, that must be equal to 1. Because these two guys, the first integral and the last integral, are going to be equal to 0. Now here, let me take advantage of the linearity of integrals. So I'm going to factor out that. Okay. So if we find this integral here, that's going to give you the reciprocal of c, right? Agreed? Okay. Now, I want you to take a close look at this expression. Finding that integral is not that hard, but it could be time consuming. But I'm going to show you a trick that we're going to be using in the future, right? It's a trick that is frequently used in Bayesian statistics. So I might as well show you this trick. I'm sure that you have seen it before, but maybe not. Maybe you don't remember it, or anyway, just let me show you. As I said, it's a very popular trick. We're going to be using this idea frequently in our Bayesian statistics course. Okay, so take a look at what's inside that integral, the integrand, right? So this guy here, this expression here, in probability theory, I'm sure that you discussed a distribution function, a particular distribution for a random variable called a beta random variable. Okay, so let me remind you what's the PDF for a random variable with a beta distribution. Okay, so beta, let me use let me use f of y. F of y represents a PDF of a beta distribution. Let me use x because we're using y for this one here, right? Okay, so anyway, the PDF of a beta distribution looks something like this. It's going to be the function capital gamma evaluated at alpha plus beta divided by the gamma function evaluated at alpha times the gamma function evaluated at beta times x to the power alpha minus 1 times 1 minus x to the power beta minus 1. Okay? and the support, the the region where the PDF is non-zero, is 0, 1, the interval 0, 1. It could be a closed interval or an open interval. In this case, we know that it's that a point or 2 points won't make a difference. So in this case, these are included. So let's include them, right? Less than or equal. So greater or equal to 0, less than or equal to 1. Okay? Now, remember that gamma functions evaluated, well, the gamma function evaluated at an integer n is going to be the same as n minus 1 factorial. So let me remind you about that. Recall that if n is an integer, a positive integer, then the gamma function evaluated at n equals n minus 1 factorial. Okay? Okay. So now I want you to compare the expression of the PDF of a beta distribution with parameters alpha and beta with the one that we have here, right? So we have the argument of the function, in this case x, in that case y, to the power something times 1 minus the argument of the function, in this case x, in that case y, to another power, and that the interval of interest is the 0, 1 interval. So this guy seems to be a member of the beta distribution family, right? So again, going back to what we know about legit PDFs, we know that if you integrate a PDF over its entire support, right, so the result is going to be 1. Okay? So what I want you to see here is that we could take advantage of that to find this integral. Okay? So let's make this guy here, that integral, look like a legit probability distribution, okay, like a beta. Okay, so this would be the same as, we could rewrite this like y squared is the same as y to the power 3 minus 1, right? 4 is the same as 5 minus 1, right? So now this is similar to this, right? Okay? Okay. Now, next step. Well, if we had that constant inside that integral would be, if we had this constant and this expression here, the integral from 0 to 1 of a constant that looks like this with the appropriate alpha and beta, right, it would be just 1. So let's try and complete the expression that we need. So it would be just note that in this particular case alpha would be 3 and beta would be 5, right? So it would be the gamma function evaluated at 3 plus 5, gamma evaluated at 3 times gamma evaluated at 5, right? And remember, these are just numbers, these are just constants. Okay, so now the thing is that we multiplied by this, we divided by this. So if we are going to be doing things legally, right, if we don't want to do anything inappropriate, what we have to do is, you know, multiply by the reciprocal here, because then this is just a 1, right? If we do that, hey, I divided by gamma evaluated at 3 and gamma evaluated at 5. Well, if you divided by that but multiplied by that same quantity, these cancel out. And the same goes for gamma evaluated at 3 plus 5, right? So this is just a 1, so we're not changing anything, it's legal, right? But now note that what we have is that this is a gamma with parameters alpha equals 3, beta equals 5, right? So this nasty looking integral is just a 1 times this. Okay, times 1. Okay, and this is the same as gamma. The gamma function evaluated at 8. Now, using what we know about gamma functions evaluated at integers, gamma evaluated at 3 is the same as 2 factorial. The other one is going to be 4 factorial. The one at the bottom, 7 factorial. Make sense? Okay. So, this guy here would be the reciprocal of the constant c that we need, right? Okay. So now let's try and find that constant using r. Okay? Okay, give me just a sec. Okay, so let's launch R and let's find that constant. So what we have here is just 2 factorial, right, times 4 factorial divided by 7 factorial. Okay, so if you want to find the factorial of 2, that's it, just use the built-in function factorial, right? So what we need here is 2 factorial, we need 4 factorial, and we want to divide by 7 factorial. Okay, right? So but this guy here is the reciprocal, right, of that constant that we want. Okay, so if we want c, the truth is that what we want is 7 factorial divided by 2 factorial times 4 factorial, right? Okay, so let me just find it like that directly, right? Because the one that we really want is C, right? Not the reciprocal. But anyway, what I wanted you to see with that is that sometimes, right, it's a good idea to remember those, we call them kernels, right? Meaning the expression of a PDF up to a constant, that's what we refer to as a kernel. It's useful to remember those kernels to find those integrals, right? So anyway, so in the end, what we have is that C happens to be 105, right? Okay, because that would be, 7 factorial divided by 2 factorial times 4 factorial. Make sense? Okay. Later I'm going to also show you how to do it another way using R. So we have that constant C. So now that we have that constant C, right, we're done with part A, but what we would like to do here is finding the next part is finding the expected value of y. Okay, so again, first let's do it by hand, and then we're going to do it using R. Okay, so expected value of y. We know that the definition, if you will, for a continuous random variable, the expected value is going to be this. Expected value of a continuous variable y is just the integral from negative infinity to infinity of y, f of y, right? Okay, so we know that. Okay, so let's use that expression. So in this case it would be the integral from negative infinity to 0 of 0 plus the integral from 0 to 1 of, now we know it's going to be 105 times this. Okay, so we know that this guy is the only part that is going to matter, right? So let me be lazy here. I know that just like what we had here, we're going to have 3 integrals. It's going to be y times 0, y times this, y times 0. So the only one that matters is this one here, right? So it's the only one that I'm writing down here. Let me copy paste this one, because that's going to be useful. But now we know that the constant C is 105, right? Okay. So so this is y times 105 times this. Okay, makes sense? We're just applying the definition, if you will, okay, of expected value for a continuous random variable. So note this will be the same as this, right? It's going to be the integral from not what I wanted to do here, right? Integral from 0 to 1 of 105 times almost this, and instead of y squared we're going to have a cube here, dy. So now, and that's why I said that idea of completing expressions for legit PDFs inside an integral could be very useful, and we're going to be using that trick very frequently whenever we have a chance to do that. Okay, so let me factor out that 105. Let's repeat the trick, right? I just factored out that 105, but now when we see this guy we go, that looks like the kernel of beta, right? Meaning the expression of a PDF of a beta distribution, well, or a random variable with a beta distribution up to a constant, right? So let's rewrite this. This will be the same as y to the 4th power minus 1. 4 is the same as 5 minus 1, right? And now what we realize is that, well, this could be transformed into a beta with parameters alpha equals 4, beta equals 5, right? So let's do that. So we have the gamma function evaluated at 4 plus 5 divided by the gamma function evaluated at 4 times the gamma function evaluated at 5, right? But again, we want to you know, just we don't want to change things, right? We just want to multiply by a1, and then we are not doing anything wrong. So let's just let me multiply by gamma evaluated at 4 by gamma evaluated at 5, and this is the one that we want here at the bottom is gamma evaluated at 9, right? But again, the point is, let me put this guy in the next line. The point is that now this guy inside our integral is just a beta. It's the PDF of a beta distribution with parameters alpha equals 4, beta equals 5. This integral is just equal to 1, and then we have basically the expected value, right? So this is just going to be 105 times this, and again we're going to be using that property of the gamma function, that gamma evaluated at a positive integer is just at a positive integer n is just n minus 1 factorial. So in this case that's gamma evaluated at 4 is just 3 factorial. This guy is going to be just 4 factorial, and this guy is just going to be 8 factorial. Gamma evaluated at 9, right? Now let's use R here to help us with the calculations. 105 times factorial 3 times factorial 4 divided by factorial 8, right? So that's it. So 0.375. Okay. So now let me show you how we can use R to do this. First we wanted to find that constant, right? let's go back to the original problem. We wanted to find the constant c that made that expression a legit PDF. So if we found the integral from 0 to 1 of y squared times 1 minus y to the fourth power, then the reciprocal would be our c, right? Okay. So just like before, I think we did this in another video, but let me show you again. So let me define f as a function with argument y, then those curly brackets, and then I want y squared times 1 minus y to the fourth power. That's our function f. Okay. Now I want to integrate f, the lower limit of my integral is 0, right? The upper limit of my integral is 1. Okay, so that is you know, the reciprocal of c, right? So I guess we could try and do this 1 over that. Oops. Well, then let me do it just like that, like this 1 over what we obtained here. Okay, 105. Make sense? Okay, so that would be another way of solving the problem if you have access to R, right? But as I pointed out, it's important to be able to do things by hand here to set it up, especially for the final exam, because you're going to be doing things by hand. Okay? Okay, so we checked, and yeah, our constant c is going to be 105. Now let's check the value that we obtained for the expected value of y. Okay? So note that now the integral that we want is the integral from 0 to 1 of 105 times y cubed times 1 minus y to the fourth power. Okay? Okay. So now let me define another function. Let me call it g. G is going to be a function. The argument is going to be y, open and close curly brackets, then 105 times y cubed times 1 minus y to the fourth power. Okay. And now we want to integrate g. The lower limit of our integral is 0, the upper limit is 1, and it's 0.375, just like what we obtained by hand. Okay? Make sense? Excellent. So let's summarize what we did here. So again, we used properties of probability density functions to find that constant, that missing constant. Property that we used is that the integral from negative infinity to infinity of a legit PDF must be 1. And then to find the expected value, we just, used the definition basically of expected value for a continuous random variable. So the integral from negative infinity to infinity of y times the PDF. And something that we learned along the way also was that trick of completing those integrals, make them into legit PDFs, and well, then if you're integrating a legit PDF over its entire support, then what you end up with is just a 1. So we used that trick a couple of times here, and finally we just checked our work using R. Okay, we defined a couple of functions and used this built-in function, this special command integrate, to find z, that missing constant, and that expected value for our random variable of interest. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.